Having completed the medium-range jet transport load sheet, Part A, we will now input the appropriate data into the trim sheet, Part B, which deals with the distribution and trim positions. This will enable the pilot to establish the zero fuel mass and takeoff mass centre of gravity position, expressed as percentage mean aerodynamic chord, for the combination of passengers, cargo and fuel load. The landing mass centre of gravity position is seldom required because it will remain within limits due to the fuel usage during the flight. Before we enter any data, we must understand the use of the scale in the cargo, passenger and fuel boxes. Let us work through an example on screen to see how it works. Starting with the dry operating index of 45.0 located on the top line, drop a vertical line down to the centre of the box immediately underneath. And observe the arrowed box with pitch 1000 kilograms, which indicates the value of the scale, so 1 unit equals 100 kilograms. The arrowhead indicates the direction of movement. In this case, the mass is 600 kilograms, therefore we have to move 6 units left. Continue the pattern by dropping a vertical line down to the centre of the next box and move right 18.5 units for 1850 kilograms. The next step is to drop a vertical line down to the centre of the next box representing the number of individual passengers in the compartment, 1 unit representing 1 passenger. There are 14 in this compartment, so we have to move left 14 units. This method is continued until all of the cargo and passenger loads are entered. Having seen how the index system works in Part B, we can now work through the whole thing to finally establish the required centre of gravity positions. So we've seen that the starting point is at the very top of the trim sheet, where we enter the crew details and dry operating index, DOI 45.0, and drop a vertical line down to the centre of the box below. Notice the entry of 3,305 kilograms in the left-hand side of this box, which represents the limiting mass for hold 1. Each box will contain the limiting mass for that compartment. Put in the hold 1 box, the mass 600 kilograms, and starting from the previous vertical line position, move left 6 units to represent 600 kilograms and drop a vertical line down to the next box below. Now enter 1850 kilograms in hold 4 box, and from the previous vertical line move right 18.5 units and drop a vertical line down to the next box below. Continue by entering the passenger numbers in each compartment from OA through to OG. Starting with OA, enter 14 and from the previous vertical line move left 14 units and drop a vertical line to the box below. This brings us to OB, and entering 12 in the box, we move from the vertical line left 12 units and drop a vertical line to the box below. In compartment OC, enter 24 and from the vertical line move left 2.4 units and drop a vertical line to box OE, passing through the box OD, which has no effect on the centre of gravity. In compartment OE, enter 24 and from the vertical line move right 2.4 units and drop a vertical line down to the box below. And in box OF, enter 16, then move right 16 units and drop a vertical line down to the box below. The final entry for the passenger load is in box OG. Enter 16 and move right from the vertical line 16 units and drop an extended vertical line through the fuel index line and continue into the centre of gravity envelope. At this point we have established the zero fuel mass index. In order to establish the takeoff mass index, we must make an adjustment to the zero fuel mass index. This is done by applying the index units for fuel mass found in the fuel index correction tables for the medium-range jet transport in CAP 696. The takeoff fuel from our load sheet, 14,500 kilograms, cannot be located exactly in the fuel correction table, but the note at the bottom states that we must use the next higher mass. In our case, we can use the index for 14,580, which will give us an index of minus 12.9 units. In the fuel index box, enter the index of minus 12.9 units, and from the vertical zero fuel mass index line, move left 12.9 units and drop an extended vertical line down into the centre of gravity envelope. We are now in a position to locate the takeoff mass centre of gravity in the envelope. Locate the takeoff mass of 62,170 kilograms from the load sheet and the vertical axis on the left of the envelope. From that point, extend a horizontal line to the right to intersect the takeoff mass index line in the envelope. Where they intersect, read off the takeoff mass centre of gravity as 18.3% mean aerodynamic chord. Enter this value in the box at the top left of the trim sheet labelled MAC at TOM. To find the zero fuel mass centre of gravity, we must first locate the zero fuel mass, 47,670 kilograms, on the vertical axis on the left of the envelope. From that point, extend a horizontal line to the right to intersect the zero fuel mass index line in the envelope. Where they intersect, read off the zero fuel mass centre of gravity as 22.35 mean aerodynamic chord. The takeoff stabilizer trim setting for flap 5 degrees is established inside the centre of gravity envelope under the heading For Crew Only, Stab Trim Units for Takeoff, Flaps 5 Only. This is achieved by using the takeoff centre of gravity position and where it intersects somewhere between the figures circled 3, 4 and 5 in the envelope. Using the previously calculated takeoff centre of gravity 18.3% mean aerodynamic chord, drop a line down parallel to the adjacent line and where it intersects between the 3 and 4 units is the trim setting for takeoff, in our case 3.8 units. If flap 15 degrees is the required flap setting for takeoff, then the trim unit for centre of gravity position table in CAP 696 must be used. This was covered in the introductory lesson on medium-range jet transport. In any mass and balance exam, it is very unlikely that students will be asked to complete either an entire Part A or Part B of the medium-range jet transport load and trim sheet. The questions asked will generally concentrate on sections of the load and trim sheet, and we will work through a typical question as an example. A typical example question would ask us to determine the dry operating index using the centre of gravity envelope in Part B of the medium-range jet transport load and trim sheet, from a given dry operating mass and centre of gravity. In the envelope, draw a horizontal line from the mass of 35,000 kilograms to a point where it meets the 16% mean aerodynamic vertical line. And where the intercept occurs, drop a vertical line down to read 45 units on the bottom scale, which is the dry operating index. We have now finished the lessons on completing both Part A and Part B of the load and trim sheet for the medium-range jet transport contained in CAP 696. In Part A, we determined the limiting maximum takeoff mass and from that the limiting allowable traffic load. We calculated the underload, which indicates whether there is any spare capacity for last-minute changes, and showed the distribution of passenger and cargo masses. Finally, in Part A, we calculated the actual zero fuel, takeoff and landing masses and checked them against their limiting values. Plotting the mass values of passengers, cargo and fuel in Part B, we saw how each mass in turn progressively affected the position of the centre of gravity. Finally, to complete Part B, we determined the centre of gravity in terms of percentage mean aerodynamic chord for zero fuel and takeoff mass, and checked they were within the constraints of the envelope.